In crewed spaceflight, rescue usually cannot arrive from somewhere else. A spacecraft may be minutes from the ground, days from Earth, or attached to a station that has become the emergency. We are here to determine the GOAT of crewed spaceflight crisis recovery operation. The field is crewed spaceflight crisis recovery operation. Survival depends on whatever machines, procedures, people, and spare capacity are already in the chain. This field begins when a crew faces an immediate threat to life and ends only when everyone reaches safety. It excludes routine malfunctions, successful missions with merely uncomfortable moments, and disasters from which no recovery was achieved. The question is not which accident was most dramatic, it is which successful recovery was most complete. Spacecraft are systems of systems. Oxygen may also feed power generation. Electrical power may control cooling, guidance, communications, and valves. Attitude control keeps antennas pointed and trajectories usable. One failure can therefore remove the very tools needed to diagnose the next failure. Distance changes the problem. Near Earth, a crew may abort and land. On a station, another vehicle may offer an escape route. Farther away, physics sets the timetable, and no aircraft or rescue ship can shorten it. The crew must keep a damaged system alive long enough to meet the planet again. The comparison turns on 6 things: how little survival margin remained, how long the danger lasted, how many failures cascaded together, how much improvisation exceeded the original design, how tightly crew and ground had to coordinate, and what later missions learned. 4 recoveries meet that standard. Each solved a different version of being trapped above Earth. In March 1966, Gemini 8 began with a triumph. Neil Armstrong and David Scott completed the first docking of 2 vehicles in orbit, joining their capsule to an Agena target. Then the combined spacecraft began to roll. At first, the crew reasonably suspected the target vehicle they had just captured. The roll grew worse. Armstrong and Scott tried to stop it with Gemini's orbital maneuvering thrusters, but the motion returned. They decided to undock, expecting separation to remove the source. Instead, the capsule accelerated into a violent tumble, revealing that the fault had been aboard Gemini all along. A stuck thruster was firing continuously. The capsule approached 1 revolution each second, fast enough to blur vision and threaten loss of consciousness. Armstrong shut down the entire orbital control system and switched to the separate thrusters reserved for re-entry. That stopped the spin. The choice saved both astronauts, but it spent roughly 3/4 of the re-entry control propellant. Mission rules now required an immediate return. The spacewalk and the rest of the flight disappeared from the plan, and Gemini 8 splashed down after a mission lasting less than 11 hours. Gemini 8 is the purest display of rapid piloting in this comparison. The crew identified a false assumption, changed control systems, and ended a lethal rotation before their bodies failed. Its limitation is scale. The decisive emergency lasted minutes, close to Earth, with an independent backup system that still worked exactly as intended. In September 1983, Vladimir Titov and Gennady Strekalov sat on the launch pad inside the Soyuz T-10-1 spacecraft. Fuel began spilling near the base of the booster, and the rocket caught fire. The crew could not simply open a hatch and run through the flames below them. Their answer was the launch escape system, a tower designed to pull the crew capsule away from a failing rocket. Fire damaged normal links, so ground controllers had to transmit the abort through an alternate path. Seconds before the booster exploded, the escape motors tore the capsule upward. The acceleration was brutal, but brief. The capsule separated, deployed its parachute, and landed with both cosmonauts alive. A machine that engineers hoped never to use had performed its one job under the exact conditions that justified its existence. That makes Soyuz T-10-1 a masterpiece of pre-planned escape. It also sets its boundary. The system removed the crew from danger rather than asking them to operate inside a wounded spacecraft for days. The recovery demanded seconds of correct design and command, not a prolonged reinvention of the mission. On June 25, 1997, the crisis came to the crew's home. During a test of manual docking equipment, the uncrewed Progress M34 cargo vehicle approached the Mir space station. It struck a solar array, and then the Spectre module hard enough to puncture the station's pressure hull. Air began escaping into space. The crew had to seal Spectre away from the rest of Mir, but power cables ran through the hatch. Disconnecting and cutting them cost precious time while pressure fell. The hatch finally closed, preserving breathable air in the surviving modules and abandoning Spectre to vacuum. The collision also took much of Mir's electrical supply. The station began to tumble, and its central computer shut down. In darkness and reduced power, American astronaut Michael Foale estimated the station's motion by watching the stars. The crew and controllers then worked to restore attitude and rebuild a usable power network. Mir did not become healthy in one heroic minute. Its occupants continued living and working inside a damaged outpost, while Russian and American teams planned repairs, reconnected solar arrays, and recovered systems over the following weeks. The rescue was not an exit. It was the rehabilitation of the only shelter available. This is the strongest rival. Mir combined a hull breach, decompression, power loss, uncontrolled motion, damaged computing, and international coordination. Yet the crew remained in low Earth orbit, with a docked Soyuz available for evacuation and later vehicles able to bring people and equipment. The station was wounded, but Earth was still close enough to help. Apollo 13 is the GOAT of crewed spaceflight crisis recovery. Jim Lovell, Jack Swigert, and Fred Haise launched in April 1970 to attempt the third crewed lunar landing. Their spacecraft was not merely a vehicle. For most of the journey, it was the only habitable place between Earth and the Moon. 2 days into the flight, a routine command to stir the service module's oxygen tanks triggered an electrical failure, and the rupture of oxygen tank number 2. The blast damaged the neighboring system, and oxygen began venting into space. The crew heard a bang, saw warning lights multiply, and watched pressure readings collapse. The oxygen was not only for breathing. Apollo's fuel cells combined oxygen and hydrogen to produce electricity and water. As the oxygen supply disappeared, power generation and water production were disappearing with it. The lunar landing was over, and the command module could no longer remain fully alive without consuming the batteries reserved for re-entry. Mission Control and the crew shut down the command module and moved into the lunar module, Aquarius. It had been designed to land 2 people on the Moon, support them briefly, and return them to lunar orbit. Now, it had to become a lifeboat for 3 people and preserve the command module for the final descent through Earth's atmosphere. Apollo 13 had earlier left a free return trajectory, a path that would naturally loop around the Moon and back toward Earth. Aquarius supplied the engine needed to regain that safer route. Its descent engine, intended to lower the module toward the lunar surface, instead became the propulsion system for bringing the entire combined spacecraft home. Aquarius was provisioned for 2 astronauts for roughly 2 days. It now had to support 3 for nearly 4. Every consumable became a budget: oxygen, cooling water, battery power, and the chemical cartridges that removed carbon dioxide from the cabin. The crew reduced electrical loads until the spacecraft became cold, dim, and wet with condensation. Carbon dioxide became the most visible design mismatch. The command module carried square lithium hydroxide cartridges. The lunar module accepted round ones. The crew had plenty of chemical capacity trapped inside parts that would not fit, an engineering problem, so ordinary in shape that it sounded absurd beside the Moon. Inders on the ground assembled an adapter using only items known to be aboard: plastic bags, cardboard, a hose, tape, and a sock. They tested the procedure, read each step to the crew, and the astronauts built the device in flight. The improvised mailbox pulled the carbon dioxide level back down. That fix did not end the emergency. Water was rationed. Electrical power had to last until re-entry preparations. The cabin temperature fell to about 38 degrees Fahrenheit, and moisture collected on surfaces. Haise became ill. The crew endured the return in conditions that made every checklist slower and every mistake more expensive. You also became harder. Debris around the spacecraft interfered with star sightings, while venting and uneven heating disturbed its attitude. The crew performed engine burns with limited electrical power, and at one point used Earth in the window as a reference. Each correction had to be calculated on the ground, translated into procedures, and executed by exhausted people. Before re-entry, the command module had to wait from a shutdown. No Apollo crew had practiced in flight. Teams and simulators developed a new power-up sequence that stayed within the remaining battery limits. After the service module was jettisoned, the crew finally saw how much structure the explosion had removed. Their margin had been thinner than the instruments could show. Aquarius was released, the command module entered the atmosphere, and radio contact vanished during the expected communications blackout. On April 17th, Odyssey descended under 3 parachutes and splashed down safely in the Pacific. 6 days after launch, all 3 astronauts were back on Earth. Mir recovered a station through sustained ingenuity, but Apollo 13 combined deeper isolation, a fixed celestial timetable, cascading losses of oxygen, power, water, heat, propulsion, navigation, and cabin chemistry, plus a return vehicle that had to be preserved while shut down. It also had advantages: an intact lunar module, extensive redundancy, and exceptional teams. That qualification strengthens the verdict. The GOAT was not a lone miracle. It was the preservation of options until disciplined engineering could turn them into a way home.